In section 12.5, we're going to learn about arc length and curvature in 3 dimensions. Recall that in section 10.3, we learned to solve the arc length of a smooth plane curve. The method we used there is essentially what we're going to use today. Basically, if C is a smooth curve given by R of t equals x of t plus y of t plus z of t on closed interval from A to B, then the arc length of C on the interval is just arc length S equals integral of square root of derivative of x squared plus derivative of y squared plus derivative of z squared integrating from a to b. And that huge chunk of formula is essentially just the integral of magnitude of derivative of curve function r of t integrating from a to b. To use this function, we have this example question where essentially we're just plugging in that formula. Find the arc length of r of t equals 2 sine ti plus 5tj plus 2 cosine tk on closed interval -10 to 10. From the question, we can recognize that the parametric equation of x sub t is just 2 sine t, y sub t is just 5t, and z sub t is just 2 cosine t. And in order to find the arc lengths, we have to get their derivatives. X sub t derivative is 2 cosine t. Derivative of y sub t is just 5. And derivative of z sub t is -2 sine t. And then we can plug in the formula. Arc length s equals -10 to 10 integrating. And the function we're integrating is just square root of 2 cosine t squared plus 5 squared plus -2 sine t squared, and then dt. From there, you get -10 to 10, 4 cosine squared t plus 25 plus 4 sine squared t. From the trigonometric identities we learned before, you can simply tell that 4 cosine squared t, cosine squared t plus sine squared t plus 25, and this part, it's just 4 because cosine squared t plus sine squared t is just 1. And then we get -10, 29 dt. And this is, in the end, just 20 square root of 29. Next, we're going to learn about arc length function. The definition of arc length function goes, let C be a smooth curve given by r sub t on closed interval a to b. For t greater or equal to a, smaller or equal to b, arc length function is given by s sub t equals integral from a to t, magnitude of derivative of r sub u du. So essentially, why arc length function is important is that we want to use a function to capture the motion along a curve. And with this function, we can calculate the arc length from any given point to the end point. And something worth to notice is that S here is called the arc length parameter. We're going to learn why that is important later on. And to use the definition of arc length function, we have an example to tell us how to use it. Example 2 is that find the arc length function of r sub t equals 3 minus 3ti plus 4tj, and t is from 0 to 1. So because we know that derivative of r sub t is just -3i plus 4j, and we know that the magnitude of r sub t derivative is square root of -3 squared plus 4 squared, which is just equal to 5. Then you can have s sub t equals integral from 0 to t magnitude of derivative of r sub u du. And basically, you get from 0 to t 5 du, and that is just 5t. So now you have s sub t equals 5t. Remember that before we called s the arc length parameter? If s equals 5t, we can have t equals s over 5. And we can use this to rewrite r sub t equal into r sub s. To do that, you just plug in t equals s over 5 into the original function. And if you do that, you can get 3 minus 3 s over 5 I plus 4 times s over 5 j. Simplify, you get 3 minus 3 over 5s I plus 4 over 5s j. The reason why we rewrite is that if you actually try to find the magnitude of derivative of r sub s, you're going to get square root of negative 3 over 5 squared plus 4 over 5 squared, and that's amazingly 1. And this is not the single case. Actually, when you write r sub s every time, the magnitude of its derivative is always going to be 1. And one advantage of this is that for a smooth curve C represented by r sub s, where s is the arc length parameter, the arc length between A and B, length of arc from A and B, know that this is always going to be 1. So here it's essentially just integral from a to b 1 ds, and you're going to get b minus a, and that's just the length of the interval. So you can see now, if you use r sub s to represent the curve, when you're looking for the arc length, it's just the length of the interval. And that's just really easy to use if all the conditions are met.